Hello all, welcome to the AI driven perception learning and mapping for drones course, foundation in CNN. Now in the previous lecture we have studied about convolution operations, we have studied about pooling operations, right, and even in the previous part we went over different normalization techniques, right. Now CNNs are essentially very efficient at understanding statistical patterns and strong understanding of representation, right. However, although it is a end-to-end learning network, we do want to visualize some of these features, right. So essentially, although it is end-to-end, we want to know what is the model understanding, what are the representations it is learning. Now some filters have a human, for some filters a human interpretation is possible, but for a lot of filters it is not possible, right. But the goal of this particular lecture is to understand at which layer of CNN what kind of an understanding the model is able to get. So for a particular image, what is the understanding that the model has, what is the features that it is learning, right. Now let us say we have a classification task. Now we have this, which is an input image, right. The input image is passed into a CNN block, which could be an encoder. So this is essentially the backbone of the neural network. This could consist of convolutional layers, pooling layers, right, normalization layers, activation functions, and so on, right. Now once we have the feature as the output, since it is a classification task, we will flatten these set of features. Once we have flattened the features, we would pass it through a fully connected layer, right, and it could be a series of fully connected layer, that depends on the model and it depends on the data set, and okay, it is more of the engineering problem. Now once we have a fully connected layer, essentially the number of neurons in this particular layer, which is the output layer, let us say, the number of neurons in the output layer should be equal to the number of classes for the classification task. So let us say we have 10 classes, then the number of output neurons here would be 10, right. Now the output is passed through the softmax function, which is essentially we are converting the output into a probability distribution. Now once we have a probability distribution, right, for some classes, say C1, which is a dog class for this particular image, the probability is very high, for the other classes it is low, right. This is the overall understanding of the backbones, right. Now the goal is to understand what kind of information is represented, or what kind of feature representations are learned at various levels, right. So we have a very deep layer and we have shallow layers, and then we have layers which are intermediate, and what are the features that this backbone is able to learn. This is why we want to focus on the visualization, right. For visualization, to understand what is the focus of various filters. Okay. Now let us consider an L layer convolutional neural network with 3x3 filters and 2x2 max pooling, right. So we have a input image which is passed through a convolutional layer, which is conv layer 1, which consists of conv layer, relu layer, and max pool. Once it is passed through the conv layer, it goes into the conv layer 2, which consists of convolution layer, relu activation, and max pooling, and so on, right. So these are just some of the layers that we saw compared to the previous backbone, right. These are some of the convolutional layers. Now if we look at the filters across different layers, so let us say we have layer 1, we have layer 2, we have layer 3, right. We know that the dimension, as we keep going deeper into the backbone, the dimension will keep reducing, right. Now let us look at layer 3, let us look at the focus of layer 3, let us look at this particular element in the feature map. This element is essentially its receptive field on layer 3 is this much, which is highlighted as a 3×3 kernel, and essentially if we look at the layer 1, it is essentially it has this projection on layer 1, right. So, the intensity of activation of this particular element depends upon what happens in this patch of the feature map in layer 1, right, and this is essentially a little intuitive when we are using convolutional operation, because we are trying to compress the information, but when we are compressing the information in layer 3 does have a look or does depend on a certain patch corresponding to layer 1 and layer 2, right. Now, let us maybe try to look at it from a numerical point of view. Let us say that we have a 1×1 kernel at layer 3. Layer 3, the height and width of this particular layer is 64×64. If we look at layer 2, its dimensions would be 128×128, and for layer 1 it would be 256×256. Let us assume the neuron actually has a 1×1 kernel. Now, when we look at layer 2, this particular layer actually would have a 3×3 receptive field, right. Similarly, a 5×5 receptive field in layer 1. Now, if we use this particular formula, we can also try to get this numerically, that layer 3, if it has a 1×1 projection, the corresponding projection on layer 1 would be 5×5, right. Now, why is this important? It is important to understand because the first layer, or let us say the shallow layers, actually focus on the edges, corners and small textures, right, and this is something that we call as a low level understanding of an image. If I have an image, right, and if let us say I have an image of a car and I can see there are a lot of semantic features in the car, but the outline is a very low level feature of the car, right. The outline could not be the sole semantic information about the car, hence we call it as a low level understanding. However, like the edges are actually very important for any task, however we term it as a low level feature, right. Now, intermediate layers essentially learn medium level features, right, and the deep layers essentially learn high level features. When I say high level features, it is essentially representations which have a lot of semantic detail. Now, one thing is we can't, so if we have shallow layers or intermediate layers or deep layers, we can't say that okay, the edges are always learned in shallow layers and they are never learned in deep layers. It is not like that, but it is more abstract. Like as you keep going deeper, the semantic understanding about that particular object becomes more abstract, more high level, right, compared to a low level representation of small textures or edges or corners, right. Now, to have a proper focus or to do a deeper study into the visualization process, Fergus and Zeller actually proposed the deconv neural network, right. This is essentially a technique to map activations from the deeper layers to the input, right, and they termed this as deconvnets, which is the counter or the opposite of convnets, right, but in reverse, and this is essentially used to visualize the features. So, what do we mean by that? Let us assume that we have an input image in the convnet, right. The input image is passed through the convolution features, and as it is passed we can observe that the feature map dimension would reduce, then it would be passed through a ReLU operation, and after max spooling it would still reduce, right. So, the dimension kept reducing and at the end we had an activation map. Now, this is the operation in convnet. In deconvnet we have to do the same thing but in reverse. So, let us start from the activation map, right. Now, we have an activation map here. What we want to do is essentially unpool this activation map, right. Once we have the unpooling operation and passing it through the ReLU, because ReLU essentially just has an effect on the elements but not on the overall dimension, right. We would essentially have a similar dimension. Now, using the conv layer we would essentially want to map to the input. Now deconv nets do not have a learnable stage. The filters that are learned during the convolutional operators, the same filters are used, right, to generate a map which is similar to the input image for visualization purpose, right. So the convolve rectified unpooled activation maps with filters learned during the training process of convnet. Now let us take a deeper look into convnets. It essentially, as observed in the previous slide, has three operations. First is the unpool operation, then it is using the ReLU, and finally it is using the filters to reconstruct. The filters used to reconstruct are the same trained features in the convnet. Now essentially it is intuitive because we want to understand what the features or what the filters in convnet was understanding, right. So it is intuitive to use the same features when we are same filters when we are using it for the visualization purpose. Now let us look at the first operation, which is the unpool, which is reverse max pooling. Now in reverse max pooling, essentially it is the opposite of max pooling, right. It is to undo the effects of max pooling. Now essentially the purpose is we want to preserve the structure of the activations of the stimulus. Essentially wherever we had very high values in activation, we want to preserve that. We want to place the reconstructions of the layer above with the appropriate positions. Now if we look at the convnet operation, let us say that we go from layer 1 to layer n plus 1, right. If we are doing that, then in max pool operation essentially we will take this particular size, we will take the maximum value and put it in the feature map, and it essentially goes for different places in this particular feature map, right. So all high activation elements in the feature map are preserved. Now these values are recorded with max locations. Essentially the indices in the original feature map are recorded, right. Now in the deconv net, when we are going from layer L plus 1 to layer L using the unpool operation, essentially we have the feature map and we are trying to do the undo operation, which is we are trying to preserve the indices that these elements had in the original feature map, right. And hence what we observe is after this operation, the rectified activation map and the unpooled activation map, the points where there exists the highest activation is preserved even in the unpooled activation map, right. Now before we go into visualizations of what each layer is representing or learning, let us quickly go over the ZFnet, which is essentially the architecture they used to generate these visualizations. Now as discussed, the feature maps, so what we observe here is essentially a modified version of AlexNet, which they termed as ZFnet, right. Now this follows a very similar structure to what we discussed in the first slide. So we have an input image, we have bunch of layers which are essentially layer 1 to layer 5, which are convolutional layers. When we say convolution, again max pooling and activation functions are already there, but essentially it is an operation on a 2D feature map. Once we have this, once the operation is done, then the outputs are flattened and passed through a linear layer. Finally the output is passed through the softmax function. Softmax function essentially will convert all the output of the neurons into a probability distribution, and the number of outputs here would be 1000 because ImageNet has 1000 classes, right. ZFnet was also made to be evaluated and trained on ImageNet, right, and hence it has 10 classes. Now let us look at this architecture in a very brief detail. We are not going into the exact detail of this architecture, and also it is, as we will keep going through different papers and different visualization techniques, right, it is recommended to read those papers from the citation given below, right. This is an essential practice in deep learning and essential practice to keep reading the architectures in detail, because we are covering the architectures in a broad scope, right, but when you read the paper you will actually understand how the architecture is. Now we have an input image. In the first layer essentially the kernel has a size of 7 with a stride 2. the image size is 227, right. Now once we pass it with a kernel size 7, we essentially get this feature map, right. Now this feature map is then passed through a max pool layer, so the overall dimension decreases. Then the layer 2 essentially has a kernel of size 5 cross 5, which is a convolutional kernel. Once it is passed, again there is a max pool operation and we get to the layer 2 output feature map. Output feature map of layer 2, now essentially a kernel size of 3 cross 3 is again applied for layer 3 and so on, right. So we know that the kernel size for layer 1 is 7 cross 7, the kernel size of layer 2 is 5 cross 5, the kernel size for layer 3 is 3 cross 3 and so on, right. Okay. Now the goal of this particular deconf process, essentially we want to use the deconf net to visualize the activations on the ImageNet validation set from this particular backbone itself, right. So from the output of layer 1, from the output of layer 2, from the output of layer 3, what understanding can we get about what kind of features are learned, right. When we have convolutional layers with additional operations like max pooling and activation functions, what are the features in the image that these layers are trying to focus on, right. So let us look at the visualization of layer 1. Now before we look at the visualizations, essentially all the 7 cross 7 filter, all the 7 cross 7 patches are obtained, right. Now the top 9 of these patches are selected, which essentially have the maximum activation. Now the strongest activation values of these particular filters are highlighted in layer 1 and the corresponding pixels are observed in the input space, and these pixels essentially highlight this sort of information, which is the edges, right. So projecting each projecting each element from the activation map separately on the pixel space to understand the structure that excites this particular feature map, right. Now essentially what we observe is that in layer 1 the neurons respond to oriented edges and color, right. This is observed here. So if I observe this feature map, it is focusing more on the edges and colors, and this is something that we saw in the slide, which says that shallow layers essentially focus more on the edges, right. Now let us look at the visualization of layer 2, but for this particular purpose let us look at deconf.net, like let us use deconf.net, use the procedure proposed in deconf.net which we discussed earlier, and look at what the features are essentially learning, right. Now again we visualize, or the paper visualizes the top patches, like not all activation maps, but activation maps that have the maximum value, essentially because, as we again discussed, all activation maps or all feature maps when projected into the input space do not result in any meaningful interpretations by a human, right. And so we try to sample out and take maximum activation maps so that we can understand what it is saying, right. It also has to be interpretable for a human to say what is the semantic feature it is learning, right. Okay. Now the second layer corresponds to corners and different types of edges and different types of colors. These are something that we observe here, right. So we can observe that there is a strong activation to these particular colors, and we can see there is a very faint activation to some of these colors. So again it is not only edges, it is edges but a different type of color information, right. Now let us look at layer 3. Layer 3 looks at a more complex pattern which is observed. So as observed here, we can see if we have these kind of structures, we observe the feature map to be activated. However, if we have, so these are essentially when you have very sharp edges. So we have black and then we have a corresponding color. So we have an edge which is extremely high, right. So we will have black and we would have a very high value, let us say 200. So this is the pixel value, and essentially this edge would be highlighted, which is something we observe here, right, and so on. And again, as we keep going to deeper layers, we cannot say what exactly like the model is learning, but we understand that it gets more complex and a higher level of representation is learned, right. Now let us look at the last layer, which is the fifth layer. Now in fifth layer, essentially we also see that pose variation has much less of an effect, right. This is observed in this particular figure. We do observe that when we have the poses which change, the activation remains more or less consistent, right. So again, as we go into the deeper layers, a much more complicated high level representation of semantic information is learned, and the effects of minor changes in either the pose or the rotation is not really that significant compared to the earlier layers. Now let us also look at feature invariance. Now small features have a dramatic effect in the first layers of the model. This is something we observe, because if you see the edges actually highlight a very how do you say, the edges observed are significantly affected due to the transformations. However, this is increasingly less of an impact on the later feature layers. So feature invariance, the small transformation in feature invariance essentially has a dramatic effect in the first layers as observed in the feature map. However, as observed in this particular feature map and even in the last feature maps, their impact is essentially less significant compared to the shallow layers. Okay. Now let us also ask this question as to why interpretability is important, right. Now in order to build us intelligent systems which are essentially trustworthy, we need to build transparent models. When we say transparent model, it means it should be explainable as to why they are making certain predictions, right. In case they are making predictions which we do not know, then we do not know how to trust these models, and hence this affects our ability to deploy these models in real world applications. Now if AI systems are significantly weaker than humans and they are not reliable, then we will not be able to use them in real world scenarios, right. And hence the goal of interpretability in this particular scenario, where the AI systems are significantly weaker, is essentially to understand the failure modes, like why is it failing, why is it so brittle when we deploy it into the real world. Now let us assume we come across AI systems which are at par with humans, then the goal is to establish confidence in the users, like this is where the humans perform well and this is exactly where the AI systems also perform well. And lastly, if we come across a scenario where the AI is significantly stronger than humans, then essentially these could also be used for machine teaching, like instead of humans annotating, we know that that particular task is done better by an AI system. So we could actually have AI systems explanations used meaningfully, right. Now there exists a trade off between accuracy and interpretability, and this is something we will see in the next lecture. Now there are deep residual models, deep residual networks like ResNet, which are essentially a very deep model, right, and they attain state of the art results. However, the way we did visualization for ZFNet, which was only with 5 layers, it may not be possible to do it for this particular variant of ResNet at each layer, right, because it would give us feature maps which may not give us information which are interpretable to humans, right. So hence there exists a trade off between accuracy and interpretability. If we have models which are shallower, then we can actually do visualization and understand what are the feature maps the model is learning. If we have models which are very deep, then as the learning becomes more abstract, as the semantic information depends on very high level representations, it becomes very hard for humans to interpret what the model is learning, right. And we'll also have a discussion about this when we are talking about changing distributions. When we deploy a model in real world scenarios where the distribution keeps changing, when the model just has a very strong in domain performance or performance in training data set, but for a out of domain performance when the model's performance is very bad. Now what are the layers which are causing the failure? These are some things that the interpretability will help us, because if we know that the shallow layers work well and the deeper layers are actually an issue, then we could maybe focus more on resolving those errors. So interpretability is essential to understand, and it is also essential to dissect the model. We want to find out why the model is brittle and to get newer, more sophisticated, robust architectures. Now to do so, for interpretability we essentially have mainly two techniques, or essentially we will try to focus on mainly two techniques. The first one is essentially known as a saliency map. Saliency map is essentially we have an input and we are trying to use these maps which would highlight the region of interest for the model. So let us say that we have a photo of a dog and the model actually categorizes correctly as the photo of a dog. Now why did the model make this particular decision, right? This is what the saliency map tries to tell us, and then we have the class activation maps. So these are the two things that we would discuss in detail now. So let us start with the saliency map. Before that, let us look at these two definitions. So feature attrition essentially explains the individual predictions by each input feature according to the prediction. Essentially when it gives us an understanding of what part of the feature map is activated when it is making a particular prediction. Pixel attrition is a special case of feature attrition. Essentially we are not looking at a feature map, we are looking at the input image and saying okay, these are the features that led to the activation and hence led to the model choosing the particular class. Now given a trained model and an input, the saliency map essentially produces a heat map of the same spatial dimension as the input. However, it has higher values indicating the region that the model actually focused on to make the prediction. So an example of this is, let us say we have an image of a dog and this image is passed to the model and the model identifies it correctly. Now in this image, what part is essentially used by the model to make this prediction? Now if we observe the saliency map, we can see that the gradients around the outline is essentially activated, right. So we can see that all the features in this particular outline are activated, right. Essentially the model is looking at this particular boundary, at this particular object in the image and then making the prediction, right. So this is what the saliency map gives us. It gives us a heat map that highlights all the potential, it gives us a heat map that highlights the places where the model was influenced most when it was making the particular prediction. Now let us go over the how this is derived, and essentially we will go into the algorithm of how we can develop the saliency map. So let us look at the class model visualization. Now given an image I0 and a class C, we have a convnet, right, and the convnet has a class score function which is given as SC of I, right. Now our goal is to rank the pixel based on the influence of SC of I0, where I0 is the given image, right. Let us assume that we have a linear model for a particular class C. So SC of I, which is essentially the class score function, can be represented as WC transpose times I plus BC. Now essentially the image is represented in a vectored form, and W and BC are essentially the weight and the bias vector of the model, right. Now this is when we are assuming a linear model, we are able to approximate a linear function, right. However, we know that CNNs are essentially non-linear functions because you have activation maps and you have other operations that make it non-linear, right. Now the class score C is a highly non-linear function of I, right, and hence if we want to make this assumption, what we could do is we could essentially write the first order Taylor series expansion of SC of I at the neighborhood of I naught, right. That would give SC of I naught as W transpose I naught plus B, right, where W is essentially the derivative of SC with respect to the image I at the point I naught. Essentially the value of W is given as dou SC upon dou I at the point I naught. Now let us look at an example for the grayscale image. If we have a grayscale image, essentially the saliency maps are extracted using a classification connet trained on image labels. It works on trained connet itself. The computation is quick because it requires only one backpropagation pass. Now let us say that we have a grayscale image I0, a trained convolutional model and a class label C. Our goal is to essentially get the saliency map M, right. Now let us forward propagate I0 through CNN, which is essentially just passed I0 through CNN and get an output prediction. Now we can calculate the class score SC, which is given as f of C of I0, right. When we have SC, we compute the gradient of the class score with respect to the input image using backpropagation. Essentially W is given as dou SC upon dou I0, right. We rearrange the elements of W to match the spatial dimensions of the image, right. Now for each pixel which is at position ij, we compute the saliency map. The saliency map M of ij is given as magnitude of Wij, right. Now once we have this feature map, we can either normalize it, but essentially the crucial condition is we want to upsample the saliency map to the input resolution, right. Now let us look at the case of an RGB image. If we have an RGB image, we essentially take I0, which is trained on CNN. We want to generate essentially the saliency map, right. So we follow the same procedure. We pass I0 through CNN, we compute the class score, which is SC, which is given as the function FC of I0. We again compute the gradient of class score with respect to the input image. So W is given as dou SC upon dou I0. Now we rearrange the gradient tensor to correspond the RGB channels. Now for each pixel ij, we essentially compute the saliency value, which is the maximum gradient magnitude across the channels. It is because RGB would have 3 channels, but saliency map we only require 1 channel, because it wants to highlight where is the maximum activation, right. So that is done using 1 channel itself. We do not need 3 channels. So for an RGB image, the saliency map is essentially the maximum across all the channel, right, the magnitude of the weights. Once we have this, we can either choose to normalize the saliency map or not. However, we upsample and view the saliency map, which is M, right. Now let us look at some of the qualitative examples. These are the saliency maps highlighting the discriminative features of the image. We can see that this actually does have a structure of goose, right. We can see that this is the overall structure of one goose and so on. So essentially when we passed a particular CNN model and it made the classification of goose, it essentially looked at these particular features, right, which has the highest activation. Similar to this is the ostrich, right. It does give us an overall structure of an ostrich, right. So if we look at these structures, we can see that there must be an ostrich there, and we can see that the edges just does give us that meaning. And lastly, an example of washing machine. So we have washing machine and we have the class activation maps corresponding to it, and we can actually see that there are certain features here which actually do highlight the specific class discriminative features about washing machine, right. Okay. Now this is saliency map. Now let us look at another method which is defined as class activation map. Now CAM essentially indicates the discriminative image regions by the CNN, which is essentially a similar operation that saliency map was used to, right. Now it is proposed for identifying discriminative regions, focus on making state of the art models interpretable without essentially changing the architecture, right. So, if we have a state of the art model, we could just use CAM and we could understand what are the features that the model is learning and why is it making misclassifications. In the previous slide, we actually saw the scenario where classifications were correct. We can also do the same for incorrect classifications, right. So, I can take a cat, right, when the model predicted it to be a cat but it was a dog, and I could see what features are essentially confusing the model, right. Now, CAM, as observed by some of these qualitative figures, highlights discriminative image regions for image classes, right. So, essentially when we have a dog or this particular breed of dog, which is Briard, we can see that it focuses more on the face, right. Similarly, if we look at hen, we can observe that it focuses more on this, right, and hence to make a prediction for hen, it would always need to focus on the face. Now, for some reason, if the hen was looking at that side and we did not observe its head, then maybe the confidence would be severely affected, right. It is because this feature was not observed properly and hence the misclassification could be possible, right. Now, let's quickly go over the algorithm for computing CAM, right, and these are just straight algorithms that we should perform to generate the particular class activation map. So, the input is I, we have a trained CNN with a global average pooling, right, and we have a particular class C. Now, what we want to do is we want to get the class activation map, which is represented as MC. Now, first step is to forward propagate the image through the CNN. Once we do the forward propagation, we want to extract the features from the last convolutional layer. This is given as F. So, F of k is identified as the kth feature map, where k essentially indices the feature map. So, F1, F2, F3, which is the feature map. The x and y essentially denote the spatial location. So, if I have F11, essentially if I have F11, I would be looking at this particular element of F, right. Okay. Now, let us perform the global average pooling, which we also call as gap, on each feature map. Now, F of k is the summation of x y for all elements in x y, F of k of x y. So, essentially we are taking the summation across the height and width, which is across the x and y, and preserving the k, right. This is defined as the global average pooling, right. Now, let us compute the class score for class C. SC is given as summation k W KC Fk, right. WKC is essentially the weight corresponding to the class feature map k. Now, let us substitute the value of gap expression into the class score. So, SC is highlighted as summation k WCK, and let us put the value of Fk here. So, Fk is represented as summation xy Fk of xy. Now, let us rearrange this summation and we get the later part, right, which is highlighted, which is essentially depending only on k, not on xy, right. So, it depends on the kth index of the feature map. Now, let us compute CAM, or let us define CAM. CAM, which is represented as M, is essentially the summation of k from WKC Fk of xy. Essentially, once we get the CAM, we can upsample the CAM to the size of the input image and visualize. Now, this is similar to once we upsample the CAM and we project it or put it on top of the RGB image, we can see the grad cams as we saw earlier. Now, although this is an algorithm, this is not very straightforward. So, let us take a look at the figure. Now, this essentially highlights the operation properly. So, we have an input image, we have this backbone, we have the last layer, and we have the fully connected layer, which is essentially making the decision, right. Now, the class here is the Austrian Australian Terrier, which is essentially the dog, right? And hence the class activation map should focus on the dog. Now we define f of k as summation xy fk of x and y. Essentially, when we have the last feature map, we are taking the summation across the height and width, not across the indexes of the feature map. This is the gap operation, which is the global average pooling. Once we do that, we have corresponding weights for each of these feature maps, right? And hence we compute SC, which is the summation of k wk fk, right? This essentially is the summation of the weights with the corresponding feature map. So it is W1 times F1 plus W2 times F2 and so on, which gives us the final class activation map. Okay, now let us look at the last part, which is the GradCam. Now GradCam is essentially the use of gradients to produce a coarse localization highlighting the important regions in the image for predicting the concept. Now essentially saliency map or even the cam focus on more or less the same part, right? It focuses on localizing and highlighting the important regions in the image, right? Now GradCam can be widely used across various CNN families used for various tasks. It is not only for classification, right? So let us assume we have CNN with fully connected layers, which is for classification. Yes, GradCam can be used. If we have a VQA task, which is an image image captioning task, then the CNN we can use GradCam even for that, and we could also use it for visual question answering. So if we have CNN news for multimodal inputs for those particular tasks, also it could be used. Essentially GradCam can be used as long as there is a convolutional neural network used for any particular task, right? Now let us look at one specific question and ask what makes a good visual representation, right? Let us look at this particular image of a dog, which is the original image, and let us ask what do I mean by a good visual explanation. Now essentially it describes two parts, and this is something which we are defining it now, but it would be crucial for segmentation and detection, right? A good visual explanation is essentially class discriminative, which is, we can see that for cat it should be able to give us features which are not the same as dog. So it should have class discriminative, and it should be fine grained. It should not be coarse. When I say coarse, it can be all over the place, right? I can say that the cat has an ear here and the cat has an ear here and the dog has an ear here, right? Now when I say fine grained detail, I know that the ear on this part is of the cat, right? It is more fine grained in nature and it needs to be more class discriminative. Only then we can classify it or even segment or do object detection, but we will keep those tasks for the later lectures. Now let us quickly go over how we can get a GradCam. Now GradCam essentially uses the gradient flow equation from the last layer of the convolution, right? Now the steps to compute GradCam are similar to CAM, but of course there are certain changes there. So let us take an input image I and select the class C. We perform a forward pass, we compute YC, which is essentially the score of C before the softmax, right? Now select the target convolutional layer whose feature maps are given as AK. These are essentially the convolution map whose GradCam we want to project, right? We could have convolution at shallow layer, intermediate layer, later layers. So essentially what is the target? Now once we know the target convolution map, we can define them as AK, where K index is the feature map and U and V are essentially the resolution, the height and width of the feature map. Now let us compute the gradients with respect to the class score. This is similar to how we did even in the previous approaches. So dou YC upon dou AK, right? Once we have this, we do backpropagate these gradients from the output to the selected convolution layers. We compute the important weights using the global average pooling, which is the GAP which we saw in the last method. So alpha KC is essentially 1 by Z summation of I summation of j dou YC upon dou AKI ij, sorry. Okay. Now once we have this, we compute the linear combination of the feature map, which is summation of k alpha ck ak. Once we do that, we want these values to have elements which are of positive or non-negative, right? We do not want negative values on the image itself. So we apply the ReLU activation function. Now once we apply the ReLU activation function, essentially what we obtain is the localization map, which we call as GradCam. Now the algorithm is a little not it's not very intuitive. So let's look at image and let's understand what we are trying to do. Now the first part of the image that we see, which is essentially this part, this is essentially the classification, the pipeline for classification that we have been discussing, that we also discussed in the first slide. So we have a backbone, we have activation maps, we will flatten these vectors, we will have output, we will pass it through softmax and we will get the particular class, right. Now once we have done this pass, let us do a different pass which is based on backpropagation and try to generate this map, right. So the first step is we want to compute the gradients of the output with respect to the target convolution layer. So dou yc upon dou ak is something that we compute and hence we get the gradient maps. Now it would be dou yc upon dou yk and we have for k feature maps, right. So we would have the same k gradient maps. Now once we do that, we try to calculate alpha based on the global average pooling of the gradient maps. Essentially what we are trying to do is for each feature map we are trying to calculate a number or a weight for that feature map, right. Now finally we have this, which is the alpha ck times ak. So it is essentially the score of the feature map into the particular feature map, right. So let us assume this is my target feature map, we have a1, a2 and ak, right. We would have a corresponding score for each of these feature map, and when we perform this operation, which is summation, we are essentially doing a weighted sum. So it is alpha 1c a1 plus alpha 2c a2 and so on for all the k elements, right. Once we do it, we pass it through the ReLU activation function, upsample it and project it, and this is what we see, right. So although the algorithm is a little bit non-intuitive, essentially when we see the figure, it does give us a better understanding and we can appreciate the use of GradCam, right. Okay. Now the qualitative results are observed here from GradCam. So we can observe that if we give a VQ8 task, which is a group of people flying the kites on a beach, it would essentially look at the kites and it would give us a GradCam around it. Or else if I have a person who is having the pizza, it would essentially highlight this person and not the person behind, and even the same case for waterfall. Okay. So to summarize, in this lecture we saw the importance of visualization and understanding. We took a deeper dive into what this lecture covers, these main topics, which is visualization and understanding. We went through visualizing different layers and see what these layers understand. We also plotted the saliency maps, the GradCams. We saw the algorithms that are used to generate these maps and how they can be used again to understand if the particular CNN backbone or the particular model is able to learn the descriptive features or not. Thank you.